Thanks. Yes, it's an honor to be here. Very glad to be here. I was here last year, and it's always very inspiring to see the community of AI worldwide. Like, it's really, and so like last year I was with my Amazon AWS colleagues, and this year with IONET. And I saw some of the colleagues here, like say hi. So let's talk about what's the idea behind. So a little bit about myself. Like before joining IONET, I worked at Amazon Robotics AI, working with AI scaling. And before, I worked with my AI consultants company based in Germany. And before that, I worked in different companies back in Brazil. And one of them was an energy company that has the largest HPC cluster, a lot of GPUs, the largest in Latin America. It's a Petrobras, an oil and gas company. And back at that time, I was working a lot of distributed processing and on-premises, like Hadoop, everything on-premise. At that time, couldn't use cloud. So getting all those open source distributed processing like Hadoop, Spark, and also leveraging GPU that was not being used by the HPC cluster that those companies use for processing seismic data, to use Jupyter notebooks to use those GPUs internally for thousands of engineers. So this type of problem, like I've been dealing like for a long time, and I really like the idea of optimizing things and optimizing resource. So at IONET, we have this idea of decentralized GPU cloud. And I'm going to share some of the details and some of the challenges and how we use the array like to provide these GPU clusters based on this decentralized GPU cloud. We are sort of like the Airbnb of GPUs. So we have the suppliers, and we will see some types of suppliers, and we have the users, and the users can consume these GPUs. So because we are decentralized, we have some peculiarities, and that brings some challenges and extra challenge. And I joined IONET not in spite of this challenge, but because of these challenges. They are very interesting to work with. And then like we'll share like how we measure node reliability, because we sort of have this distributed GPU cloud, and how we customize Ray for some of the challenges we had, and some optimization effort, and some research partnerships that we are establishing, and also be opening a channel for this. So basically we had these independent data centers, crypto mining farms, and consumer GPUs on one side. And then like from the other side, we have the users that want to find GPUs. And there is a little bit of paradox, because we don't have enough GPUs for everyone, but we do have some idle GPUs, or even like some mining farms that they were using GPUs to mine Bitcoins or doing some activities, and they realized that they can earn more, like if they rent their GPUs for AI workloads. And actually, the founders of the IONET, they had this aha moment, like when they themselves were trying to get access to more GPUs from public cloud providers. They were having more difficulties to increase the number of GPUs, and also the cost was higher. So they reached out to some GPU farmers, and they offer like, oh, I can pay more than what you get using like mining. And then it was also a fraction of the cost what they would pay for a public cloud. So, and after like solving the problem for themselves, they realized, oh, this is a generic problem. Like everyone wants more GPUs, more affordable GPUs, and we don't want idle GPUs in the world. So it's a problem that needs to be solved, and it's an interesting problem. So to provide the GPU in a way that makes sense, one of the ways to deliver is via Ray GPU clusters. So I'm going to show a little bit of the public information that is available that we call the IO Explorer. It shows like all the workers that are available, the cards are available like for everyone. So the list of device, the quantities. So we have like more than 300K verified GPUs, which means that they were tested, they onboarded to the network, they kept the connectivity, and they also executed some proof of capacity, proof of work, to prove that they are really that model. And then like I'm going to show some more details of how we measure their health long time. So just to have a notion, like they are gel distributed nodes. And I'm going to zoom in a bit here on the Pacific Coast where we are. And like sort of you get to know what are GPUs that are available ready to create a cluster on top of them. And here's a number of clusters. And when we say like GPU is available, it's like they were tested like within the current hour or in the last hour. We have more verified GPUs, but they might be turned off, or maybe they went offline for some period. So we only consider those that are really right to join the cluster. So you have like this list of workers. So their type, like their status, if they are hired or not, and in the source. So we have different also source that were already available on the Web3, that render network and Filecon. So we bootstrap all these partnerships. And then this is a view like of a specific device. So we measure the uptime. So we have this observability so that we make sure that worker would be in a good health when we selected to join a GPU cluster. So we capture the uptime, we do proof of works, and all the history, and also cluster joinings is everything available on the network. And like one person, like for creating a cluster, you can just add, you can use your credit card and add to the balance. You don't need to use like a wallet address or something, but the worker, those who put the worker to join the network, the way that under the hood, the way that the payments are happening is via Solana, on the Solana network, via on-chain transactions. So there are all these micropayments, and even like those workers which are idle, like they also get some reward for being available on the network. So all these under the hood, it happens on chain. But if you're joining the cloud, if you're using the cloud, you don't need a wallet address. You can use a connection directly. But for the workers, they get earned, and because these workers are distributed in more than 100 countries, they get paid on this area. So this is just like showing how it would be, like has integration with Stripe. And then this is how you would create a cluster. Yeah, you select what you're going to do with the cluster, and then you select the connectivity tier, and then you can select the GPU card, and then you can set up, and it runs up Ray cluster in 1 or 2 minutes. And why is this like? And you like the user who is creating the cluster, they pay a fraction of the cost. Because of the nature of the IONET project is built in, and those who have idle GPUs, they can just onboard to the network and streamline the offer of that GPUs. And here, like once the cluster is created, we offer like a Visual Studio and Jupyter Notebook, and also the Ray dashboard. And then like they have the credentials, and then they are ready to use, and just like the way everyone is used to use. So a little bit on the architecture. So we, for the head node, like if a worker fails, then like we replace the worker. Like there are some process running that will get to work and make it join again the cluster, a new worker. And for the head node, we don't want the head node to fail. So for the head node specifically, we are more choosy. We select from SOC 2 selected suppliers. And then once the Ray cluster is created, we set up a VPN, like we have the I/O tunnels, and then we set up the VPN so that all the nodes can communicate with themselves. And only the head nodes, like it's exposed with the I/O tunnels and with the credentials that is shared for those who create the cluster. And all like the uptime system, like to guarantee the health of the system, and the logger, some accessory components like to make everything work. And we did some changes on the array, so we spin up the array cluster using a customized array package, and also we add authentication to the array dashboard, because by default, like, you will not have authentication, but we expose with the authentication, which we provide the credentials when the person creates their cluster. So once you create it, like it's a normal interaction, you have a Jupyter Notebook. You also have VS Code. Here is an example of a distributed training using 56 nodes. So this cluster I created like in 1 minute and had all these nodes and executed. So it's a distributed training as an example. All of you is invited to join the booth, and then we can create a cluster together with A100 and other types of GPU, all created in 1 minute and with a fraction of the cost. So we have like some ongoing optimization efforts. It's like we are in this scenario, like when we select the nodes, like we want the node to have a good reliability score, which means like if a node like goes offline frequently, we don't want to select this node because it will not be a good customer experience. But beyond that, we also want to optimize the latency and all other aspects. So if you have like, say, 30K GPUs, and then there is a request to fulfill of 100 GPUs, and you want a maximum latency that you can accept for your workload. So ideally, you would remove all those from the possibility, like all of those who will have a more latency between those nodes. So you have sort of this graph, and you have the latency between all the nodes. So you want to select in a way that you respect all the maximum latency for the type of workload, and also in a way that you can fulfill future requests. Like if you only optimize for one request, you might not be able to fulfill others. So there are a lot of graph theory optimization problems under the hood, which are being worked on. And also there's the communication overhead. Like you can create a cluster with GPUs and do a distributed training. But for instance, if they are in different locations, so you will have some communication overhead and latency. So currently, this is up to the person who is creating the cluster, what type of project of workload they're going to do, and if they are going to select multiple locations, then they will have the latency themselves. The idea is that the platform can be more opinionated and sort of have some of these pieces optimized for the user. And also like even the topology and the communication protocol. Not always like you need a fully connected graph for your workload. Like if you think about distributed inference, you can have some on the different areas, and like a content delivery network, sort of like a model delivery network, and not necessarily you need a fully connected graph, and you can optimize on some communications. So this is some active research that we are aligned and that we want to extrapolate. These are examples of two recent papers, like dealing with distributed inference and also decentralized training. Like there are universities and companies working on it. And the idea is like, imagine you have a new communication protocol that optimizes this type of distributed inference. And then you want to test this, and then you could use this type of network, like at IONET. And we provide sort of blueprint, and you can reproduce even like research works, so that, okay, I want to test this algorithm with this type of works and distributions, and then we can like help advance the research in this area, because it's of interest that this type of distributed processing works well in these geo-distributed nodes and this type of network. And then I would drop down here, like we have IOG Foundation that we will be sponsoring this research in this area. So infrastructure for testing and validating this novel, decentralized, large-scale distributed, and also partnerships with leading academic and institutions that want to improve all this research which is going on, so that decentralized inference can be more and more efficient. The way I think about it is like, if we think like before pandemic, we thought that it was not possible for people to work remotely. But then the pandemic came, and then we needed to optimize our communication protocol so that everyone could work at home. So it was not the same way that people were working, but things were adapted. So it's all around the communication protocol. You don't want to, like during pandemic, you were not going to do a stand-up in person every day, so you would do it in a different way, even the frequency of communication. So it's all about the how you review algorithms so that the communication changes and optimize so that you can do some local communications and then other things and other layers of communication. So all the research around this, they work with the different protocols. For instance, one type of protocol is the gossip communication protocol, which is also, by the way, is common on office and remote work at work. So you also have the gossip protocol at work. That also happened in office, and then after with the pandemic also was adapted to work on remotely. So I would like to invite everyone like to join our booth. Like we will be here also like tomorrow, and also open for questions. Glad to hear your questions. Yes, over there.
Maybe, oh, okay, sorry, thank you. If I have 100 GPUs and I want to share the GPU in IONET, what should I do?
Okay, as a user, you want to use GPU or you want to put your GPU to be used?
I want to put my GPU in your net.
Okay, so you onboard your GPU. There is what we call the I/O worker, and then you connect through the network, and then you will let it running. So basically, it will be a Docker image that will be running. And for specific suppliers and big suppliers, we do some specific project. Like if you're going to onboard in batch, then we deal with case by cases. So if you have like H100, then like let's really talk.
Okay, I see. I get you. So basically, I need to install certain software on my computer or on my server or something like that.
Sorry?
So basically, you said if I want to onboard my GPU in IONET, and I need to do some configuration and install some software on my server.
Yes, basically you're going to run a Docker image, specifically that you will run. There is a Go launcher, and then you download from our repository, and you will let it running, the service.
Okay, I get it. Thank you.
Hi, first of all, thank you for the talk here. How do you do distributed training, like you use distributed data parallelism, DDP, or some other new concept of sharding weights, the layers of the models across different geographies, or is it about distributing in the same node? It could be 8 GPUs, 4 GPUs, or like that. So what type of distributed training we are talking about here?
Yes, if you start a Ray cluster, you do like the Ray is doing. Like, so if you're using a PyTorch, you will use DDP under the hood, and then you might consider NVCC or something. We have other types of offers, like which I did not focus here, is like bare metal servers, and then like you don't have the Ray cluster on top of it. But and here like you would use a Ray normally. Like for instance, here these are different nodes, and they are running a distributed training.
Okay, and when, like, let's say you have individual providers on the platform also with their nodes, so how is security of data handled on such nodes?
Yes, so there is this end-to-end encryption for the workers to connect. They are under a VPN, and then like all those who can join, like they need to be authenticated to the what we call IO ID. Like we run a auth0 authentication, like for the nodes to be able to join. And once they join within the VPN, like that network is in that perimeter, like you have the head node. I'm not sure if I completely answered your question, but. Yeah, I like hard questions. Like, don't worry. Okay.
Hi, thank you for the talk. My question is, what's the minimum number of GPUs I can have to put on a network? Like, do I need a cluster with some minimum number of GPUs, or can I just put my own personal computer's GPU on this network?
Yeah, you mean as a user?
No, as a provider.
As a provider, there is no minimum. We have some consumer grade, like offering like a 149, for instance, RTX 49 or.
Okay. So if there's no limit, like let's say I put my own personal computer's GPU on there, and so does like let's say a million other people, how do you utilize these kind of like very, very distributed GPUs that are in a bunch of people's houses? Like how do you handle the latency of like communicating to all these different IP addresses, moving data back and forth to these GPUs, and like splitting up a model to fit parts of models on all these GPUs? Like, can you give a sense of what the overhead, compute overhead would be for managing the parallel compute versus the compute that actually goes towards training a model?
Yes, so there will be some case like that the overhead might bring more like latency than like give return. So it's up to those who are creating. Like for some AI workloads, you need to select the right GPU or model. And for some distributed training, like sometimes even like using a specific protocol, like using Ray, for instance, might not be optimal for the type of distributed processing that you want. So this is sort of like a ongoing research area, hot area, and of very interest. Because if we think about large quantity of GPUs, like they also need a lot of energy. So if we are able to do this well, very distributed, like we also will have more possibilities on the energy and the power generation to be. They don't need to be so concentrated, which is a hard thing to have.
Do we know, like, if you use enterprise scale GPUs versus like consumer grade GPUs, what the energy efficiency is per flop? Like, is it roughly the same, or is it like with enterprise it'd be like you get an order of magnitude more flops per watt of energy or per watt of power? Is there any sort of like metrics like that are known?
Yes, that's an interesting question, and this is also like based on benchmark and the use case that you will have. So basically, like for all these configurations, we want to have these benchmarks. Even the type of VPN like can play a role. So that's something that to explore a lot. Okay. Okay, thank you.